This is the most famous equation of all time.
E is equal mc squared.
E equals mc squared.
Equals mc squared.
E equals mc squared.
But my question was, where do we actually use this equation in our day-to-day life? In this video, I will give you 3 ways you benefit from Einstein's equation every day. First, let's break this equation down to understand what does it even mean. We have E, M, and C. E is simply energy. What you should keep in mind is that energy cannot be destroyed or created. Every form of energy we use comes from transforming one type of energy into another. For example, we capture sunlight and convert it into electricity. We then use that electricity to generate heat, sound, motion, you name it. Even when you hold something, it has potential energy, and by letting it fall, when it hits the ground, some of that energy is converted into sound. You get the idea. But how was energy created in the first place? Well, after the Big Bang, galaxies and stars began to form. The food we eat, the fuel we use, in fact, all the energy we have ever used or will ever use originated from the Big Bang. Even the materials in your room, all that energy is transformed into something else, but it's never destroyed. It's still there, but we will come back to this later. Another element in the equation is M, mass. Mass is simply the amount of matter in an object. The more matter an object has, the heavier it is. But don't confuse mass with weight. Your weight depends on gravity and varies depending on where you are. For example, you might weigh 80 kilos on Earth, 20 kilos on the Moon, and 200 kilos on Jupiter. So you are not overweight, you are just on the wrong planet. However, your mass always remains the same, no matter where you are. And last but not least, we have C. C represents the speed of light, and as we explained in our previous videos, it is always constant, no matter how you measure it or from which perspective, it is always c. Now that we know what each term in the equation means, let's see what the equation actually tells us. It says that mass contains a huge amount of stored energy. Why huge? Well, because in the equation, we multiply mass by the speed of light, which is this massive number squared. In other words, we can convert anything, and I mean anything with mass, into an immense amount of energy. That's essentially how nuclear energy works. For example, if you want to see how much energy is restored in a grain of rice, you need to multiply its mass, which is only 0.03 grams, by speed of light, which is this massive number, squared. When we do the math, you can see it comes out roughly 2.7 trillion joules, which is a lot of energy. To put things into the perspective, that is enough energy to power an average household for 75 years. If you increase the mass with medium-sized pineapple, which is only 1 kilogram, you can power the whole New York City for 18 years. And with almost a 7-ton truck, you can power the whole planet for 1 entire year. I made a whole video and explained why we don't do this. You can join the community for completely free and watch the video. Okay, now that you know what E equals mc squared is, where do we actually use this equation in our day-to-day life? One way we use this equation in our daily lives is to keep our food clean and safe. Here's how. This is cobalt. When we put it in a nuclear reactor for 24 months, it turns into the radioactive version of itself. And since it's now unstable, it naturally starts to decay over time. As it decays, it loses tiny amount of mass. As we said earlier, every bit of mass has energy. A lot of energy. Because even though the mass is small, we have to multiply it by a very big number, which is the speed of light, squared. The energy from that lost mass is released as a powerful gamma rays. We use that gamma rays to kill bacteria, mold, and pests in food. It's like giving food a protective shield against spoilage, helping it stay fresh for longer. That's why irradiated food takes longer to rot and it's safer to eat. And no, the food itself never becomes radioactive. In fact, next time you go shopping, you can check to see if your food is irradiated. If you see this sign on the packaging, it means that it has been. Another way we use Einstein's equation in our daily lives is in smoke detectors. Well, if you have ever purchased a smoke detector, you probably know that there are two kinds of them. Almost 85% of smoke detectors in the US are ionization alarms. In this type of smoke detector, there is a tiny piece of radioactive element called americium-241. The name doesn't matter. It's unstable and it decays over time, meaning it's shooting alpha particles and ionizing, or simply put, charging the air above it. That creates an electric current, and the alarm can measure that. Once smoke particles come in, they interfere with the alpha particles, and as a result, the flow of electricity drops, which causes the alarm to go off. Here's where the equation comes in. During the initial designs of these kinds of smoke detectors, engineers used Einstein's equation to calculate how much energy would be released per decay. Because, again, as that radioactive element decays, it loses mass. And since we know how much mass is lost, we can calculate the amount of energy released per decay. Once we have that, we can compare and check if it's enough to ionize the air molecules. If it's too weak, there will be no electric current for the detector to monitor. If it's too strong, it could create an unnecessary radiation risk and make the detector unsafe. Another way we use Einstein's equation in our daily lives is in PET scans. Just like before, we are working with a radioactive element. We inject a small amount of it into the patient's body. What type of radioactive element we inject depends on what we need to look at. For example, when detecting cancer, we use a radioactive element that cancer cells easily take in. Therefore, after injection, all the injected elements gather inside the cancer cells. And since it's unstable, we know it decays over time. As it decays, it releases a positron. This positron then collides with the electrons in our body and annihilates them completely, converting 100% of their mass into energy. All of that energy is released in the form of two gamma rays, which travel in opposite directions. The PET scanner detects these gamma rays, determines where they originated, and creates a detailed image of exactly what is happening in the patient's body.